All right, today we're jumping into some really fascinating research that tackles one of the biggest challenges in medical AI. How do we get these incredibly powerful systems to not just give us an answer, but to explain their reasoning in a way we can actually trust?
So, let's set the stage, because this isn't just an academic problem. Chest x-rays are everywhere. They're the most common medical image taken worldwide. But we have a serious bottleneck. There's a global shortage of radiologists, which means the ones we do have are swamped. We're talking huge workloads, fatigue, and that can lead to diagnostic errors. It's a really high-stakes situation that's just begging for a better solution.
So here's how we're going to break this down. First, we'll talk about the black box dilemma. You've probably heard that term. Then we'll look at the clever solution this research proposes, uniting pixels and prose. After that, we'll dive into the hard data to see if it actually works. Then we'll look at how it explains itself. And finally, we'll talk about what this all means for the future of AI in the clinic.
Okay, so let's get right into the heart of the matter, the challenge of trusting an AI when the stakes are, quite literally, life and death.
And this is really the central question, isn't it? We have these deep learning models that can look at a chest x-ray and find things with incredible accuracy, sometimes even better than a human. But if the AI just spits out a diagnosis with zero justification, how can a doctor possibly feel confident acting on that information? Right, so here's the fundamental conflict. You've got these incredible tools, these convolutional neural networks, or CNNs, that are naturals at image analysis. But they are classic black boxes. You get an answer, but you don't get the reasoning. And that lack of transparency, it's a huge roadblock for adoption in hospitals. Sure, we've had tools like GradCam, which give you a heat map showing where the AI is looking, but that's only what the researchers call low-level interpretability. It tells you where, but it doesn't tell you what it's seeing or why it matters.
So how do we fix this? Well, that brings us to the core innovation of this research, a new kind of framework that thinks in more than one dimension. They call it a multimodal AI framework, and really it's about fusing two different kinds of intelligence. You've got the visual analysis from the CNN, which is great with pixels, and then you combine that with the linguistic reasoning of a large language model, an LLM. The whole idea is to bridge that huge gap between a machine seeing something on an X-ray and a doctor actually understanding the clinical logic behind it.
And here's how it all comes together. First, a really powerful CNN, DenseNet 121, chews on the X-ray data. Then, step 2, GradCam does its thing and generates that visual heat map, pointing to the exact spots that caught the AI's attention. Now, here comes the magic trick in step 3. The AI's probability scores get fed into an LLM that has been trained on a massive dataset, 68,000 real-world X-rays and their corresponding radiologist reports. Finally, it all comes together in one unified report. You get the diagnosis, the visual proof, and a clear written explanation. The whole shebang.
Okay, a clever idea is one thing, but for this audience, I know what matters. Do the numbers back it up? Let's look at the results.
And this table really says it all. On the left, you've got your standard unmodal CNN just by itself. On the right, our new multimodal framework. And just look at the difference. Across every single key metric, AUC, F1 score, precision, recall, the new system isn't just a little better, it's significantly better. So it's not just more explainable, it's actually more accurate. Let's zero in on that AUC score, the area under the curve. Pumping that up from 0.891 to 0.915 is a really substantial improvement. In plain English, it means the model is just plain better at telling the difference between a healthy scan and a diseased one. And the F1 score tells a similar story. This metric is all about finding that perfect balance between not raising false alarms, that's precision, and not missing anything important, that's recall. That jump to 0.89, that signals a much more reliable and trustworthy model, which is exactly what you want in the real world.
Now this is really interesting. This chart shows where the framework made the biggest difference. It turns out the system got a massive performance boost when diagnosing the rarer, more difficult conditions. You know, the exact kinds of cases where a human expert might actually want a reliable second opinion.
And here's the kicker. All of this extra accuracy and explainability doesn't slow things down. The system can process an image and generate the full report in just 1.8 seconds. That's fast enough to keep up with the demands of a busy clinic, making it a truly practical tool. But honestly, the true breakthrough here goes beyond just the performance metrics. It's about the quality of the explanation itself, something the researchers call dual interpretability.
So what does that actually mean? You've got this heat map and you've got this text. How do they work together to create something a clinician can actually use and trust?
This slide just nails it. The GradCam heat map shows you where the model is looking. It's the visual evidence, plain and simple. But then the LLM narrative comes in and explains what the model is seeing in that exact spot. And it does it with clinical context. One gives you the proof, the other tells you the story. It's that combination that's so powerful.
Let's look at a real example from the paper. Here we've got a case of cardiomegaly, which is an enlarged heart. First up, the visual. You can see the heat map perfectly localizes the area of concern. It's pointing right at that enlarged cardiac silhouette.
And then comes the text. The LLM translates that visual into a crisp, clinical sentence. Notice it doesn't just say big heart. It says the cardiac silhouette is enlarged relative to thoracic proportions. That is the precise language a radiologist would use. The system isn't just giving an answer, it's showing its work in the language of medicine.
Okay, so we've got a technology that's more accurate, it's fast, and it can explain itself. So what's next? What's the path to getting this into hospitals and earning the trust of doctors? Well, the big conclusion is pretty undeniable. This research shows that you don't have to sacrifice accuracy for transparency. This framework delivers on both fronts, and that directly attacks that black box problem we've been struggling with for so long.
But of course, the work isn't done. The roadmap from here involves making the system even smarter by feeding it more data, like electronic health records and lab results. Then it's about validation, doing large-scale studies with actual radiologists to see how it performs in their workflow. And finally, focusing on the crucial deployment and ethics questions to make sure it's robust, fair, and safe.
I think this quote from the authors really captures the whole spirit of the project. The goal here isn't to build a machine that replaces the doctor. It's to build a reliable colleague, one that gives you the answer, shows you the proof, and even writes up a summary for you.
And that really leaves us with a final thought to chew on. What if we're moving past the idea of AI as just a tool? This research suggests we might be on the brink of creating something different, a true partner in diagnostics. One that's not only powerful and accurate, but also transparent, collaborative, and ultimately trustworthy.